forwarding is an essential component in connecting applications and services to the internet. Without port forwarding, applications and services such as web servers are only available to devices within the same direct network. Take the network below as an example. Within this network, the server with an IP address of 192.168.1.10 runs a web server on port 80. Only the two other computers on this network will be able to access it, and this is known as an intranet rather than an internet. So you can see we have our server here and then a couple other computers. If the administrator wanted to make the website to be accessible to the public using the internet, they would have to implement port forwarding like in the diagram below. So here we can see that when someone visits this IP address on port 80, it's forwarded to this computer on port 80, and that's where we have port forwarding at play. With this design, network number 2 will now be able to access the web server running on network number 1 using the public IP address of network number 1. It's easy to confuse port forwarding with the behaviors of a firewall, a technology we'll come to discuss in a later task. However, at this stage, just understand that port forwarding opens specific ports. Recall how packets work. In this specific case, and you can see that it's just taking this and passing it along, just forwarding the connection. In comparison, firewalls determine if traffic can travel across these ports, even if the ports are open by port forwarding. Port forwarding is configured at the router of a network. What is the name of a device that is used to configure port forwarding? It's what we just mentioned. That'll be the router. Let's move on to task 2, Firewalls 101. A firewall is a device within a network responsible for determining what traffic is allowed to enter and exit. Think of a firewall as border security for a network. An administrator can configure a firewall to permit or deny traffic from entering or exiting a network based on numerous factors such as where the traffic is going, so source and destination port and address, so where it's coming from, where it's going to, what port is the traffic for, what protocol is the traffic using. So for example, has it been told to allow SSH or allow UDP, allow TCP, further things like that. You can get pretty fine-grained with these things. Firewalls perform packet inspection to determine the answers to these questions. Firewalls come in all shapes and sizes, from dedicated pieces of hardware, very common to find in businesses, so large networks like that can handle a magnitude of data, to residential routers like at your home or software such as Snort, and firewalls can be categorized into 2 to 5 categories. We'll cover the 2 primary categories of firewalls in the table below. First we have stateful and then we have stateless. Moving on with stateful. This type of firewall uses the entire information from a connection, rather than inspecting an individual packet. This firewall determines the behavior of a device depending on if the connection has been opened. So it's based on the entire connection, the entire history, rather than just that packet at that point in time. This firewall type consumes many resources in comparison to stateless firewalls, as the decision making is dynamic. For example, a firewall could allow the first parts of a TCP handshake that would later fail. If a connection from a host is bad, it will block the entire device. Again, stateful firewalls are very cool, but they're much more resource intensive. Moving on to stateless firewalls. This firewall type uses a static set of rules to determine whether or not individual packets are acceptable or if they're just going to be blocked. For example, a device sending a bad packet will not necessarily mean that the entire device is then blocked. Whilst these firewalls use much fewer resources than the alternatives, they're a lot just simpler. For example, these firewalls are only as effective as the rules that are defined within them. If a rule is not exactly matched, then it is effectively useless. So we have rules that determine these packets at this point in time, rather than considering the connection at large. However, these firewalls are great when receiving large amounts of traffic from a set of hosts, such as a distributed denial of service attack or a DDoS attack. Let's move into the questions. What layers of the OSI model do firewalls operate at? That would be, I believe, layer 2 and layer 3. Let me go ahead and check my notes real quick. There we go. Had them in the wrong order. So layer 3 and then layer 2. What category of firewall inspects the entire connection? That is stateful. Again, that's much more resource intensive. And then what category of firewall inspects individual packets? That is stateless. And there we go. Let's move into task 3, practical firewall. deploy the static site attached to this task, and then we'll go ahead and move forward. The website at 203.0.110.1 is under attack. Quickly add some firewall rules to stop the server from crashing. Packets in red are from the attacker's machine. So we have this malicious machine right here, and we want to grab its source IP, which is ending in 34. And if it has, oh, it might crash because I'm slow and explaining this. And then port 80, let me go and add the rule just so that it doesn't crash. There we go. Now we'll break this down. So we have our source and then our IP, or destination IP. And it's not going to show it, but we essentially defined where the traffic's coming from, where it's going, and then what port it's going to, and what action we're going to take. In this case, we know this is a bad or threat actor going to our website, and we want to draw off that traffic, so we don't want to actually have it continue on. And we define that rule, or that action, in our rule. So we've gone ahead and done that. We'll go ahead and submit that. I recommend watching that back one more time if you if it moved pretty quickly. Just know that, again, we need our destination, or source, destination, the port, and then what we want to do with it. Let's move into task 4, VPN basics. A virtual private network, or VPN for short, is a technology that allows devices on separate networks to communicate securely by creating a dedicated path between each device over the internet, known as a tunnel. Devices connected within this tunnel form their own private network. For example, only devices within the same network, such as within a business, can directly communicate. However, a VPN allows two offices to be connected, so we can have a VPN that forms a route between those two offices rather than just from one device to another. It allows one device or one network to communicate with another device, or another network rather. We're just creating a tunnel, so to speak. So here in this diagram, we have the network 1 here, network 2 here, and then we have network 3 with a VPN. The devices connected on network 3 are still part of network 1 and network 2, but also form together to create a private network. So these are on their own network that only devices that are connected via this VPN can communicate over. Let's cover some of the other benefits offered by a VPN in the table below. So some benefits with this allows networks in different geographical locations to be connected. They offer privacy because it is a private connection there and there's typically encryption at play. Offers anonymity because you can route your traffic throughout another region. You can encrypt that traffic and push it out a different way so it doesn't look like it's coming from you. And then there's a couple other minor benefits, but we won't get into those right now. Those are the major items. Tryhackme uses a VPN to connect you to our vulnerable machines without making them directly accessible on the internet. This means that you can securely interact with our machines. Service providers such as ISPs don't think you're attacking another machine on the internet, which could be against the terms of service, so it keeps you safe. And then the VPN provides security to Tryhackme, as vulnerable machines are not accessible using the internet, so they're not susceptible to bots in that specific way. VPN technology has improved over the years. Let's explore some of the existing VPN technologies below. First, we have PPP. This technology is used by PPTP, explained below, to allow for authentication and provide encryption of data. VPNs work by using a private key and public key certificate, similar to SSH. So you have a way that you don't have to send your key over the network. A private key and certificate must match for you to connect. This technology is not capable of leaving a network by itself, so it's non-routable. Don't worry too much about this, and all of these protocols, it's just something to know that they exist. As you advance in your career, this is something that you'll dig into further when you start examining network security at a more fine-grained level. Let's move into PPTP. The point-to-point tunneling protocol, or PPTP, is the technology that allows the data from PPP to travel and leave a network. This protocol is very easy to set up and is supported by most devices. It is, however, weakly encrypted in comparison to alternatives. And then last but not least, we have IPsec. Internet Protocol Security, or IPsec, encrypts data using the existing IP protocol. IPsec is difficult to set up in comparison to alternatives. However, if successful, it boasts strong encryption and is also supported on many devices. Again, don't worry too much about the specifics here, just know that these exist. What VPN technology only encrypts and provides authentication to data? That is PPP. What VPN technology uses the IP framework? That is IPsec. Perfect. Let's move into task 5, LAN networking devices. first, let's talk about what a router is. It's a router's job to connect networks and pass data between them. It does this by routing, hence the name router. Routing is a label given to the process of data traveling across networks. Routing involves creating a path between networks so this data can be successfully delivered. Routers operate at layer 3 of the OSI model. They often feature an interactive interface, such as a website or a console. Website's pretty common in the case of even most business routers at this point, but this is going to be what you interact with on your home network, that allow an administrator to configure various rules, such as port forwarding or firewalling. Routing is useful when devices are connected by many paths, such as in the routing or the diagram below, where the most optimal path is ultimately taken. Routers are dedicated devices and do not perform the same functions as switches. We can see that router A or computer A's network is connected to the network of computer B by two routers in the middle. So we have the network of computer A and then the network of computer B. And we have these two middle devices that are presumably also routers, given the symbol used. The question is, what path will be taken? Different protocols will decide what path should be taken, but factors include what path is the shortest, what path is the most reliable, and which path has the faster medium, so copper or fiber, so on and so forth. We've already talked about this in a previous room, so we'll go ahead and move on. What is a switch? A switch is a dedicated networking device responsible for providing a means of connecting to multiple devices. Switches can facilitate many devices from 3 to 63 using Ethernet cables. Switches can operate at both layer 3 and layer 2 of the OSI model. However, these are exclusive in the sense that layer 2 switches cannot operate at layer 3. Don't worry too much about that right now, just know that switches can either be at layer 2 or layer 3. Take, for example, a layer 2 switch in the diagram below. These switches will forward frames. Remember that there are no longer packets, as the IP protocol has been stripped onto the connecting devices using their MAC addresses. So we're just sending things onto other devices using the MAC address in this specific case. Think this is just layer 2, this is the data link layer in this specific instance. These devices are solely responsible for sending frames to the correct device. So this computer sends something here, and the switch itself has that MAC address saved in the ARP cache here, and it'll forward it along. So pretty straightforward. Now let's move on to layer 3 switches. These switches are more sophisticated than layer 2, as they can perform some of the responsibilities of a router. Namely, these switches will send frames to devices, as layer 3 or layer 2 does, and route packets to other devices using the IP protocol. Let's take a look at the diagram below of a layer 3 switch in action. We can see that there are two IP addresses. So we have 192.168.1.1 and then 192.168.2.1. A technology called VLAN, or Virtual Local Area Network, allows specific devices within a network to be virtually split up. This split means they can all benefit from things such as the internet connection that comes in, but are treated separately. This network separation provides security because it means that rules are in place to determine how specific devices can communicate with each other. This segregation is illustrated in the diagram below. So here we might have one VLAN for the sales department and another for accounting. Don't worry too much about that right now, just know that this is a way that we can divide up networks. In the context of the diagram above, the sales department and the accounting department they'll both be able to access the internet, as seen up here, but will not be able to communicate with each other if that rule is in place, although they are connected to the same switch in that manner. Let's move into the questions. What is the verb for the action that the router does? I believe that should be routing. There we go. What are the two types of switches? Separate these by a comma. Should be layer 2, layer 3, I would imagine. And there we go. Let's move into task 6, Practical Network Simulator. Go ahead and load the site, and then we're going to go ahead and complete our tasks. Deploy the static site attached to this task and experiment with the network simulator. The simulator will break down every step a packet needs to take to get from point A to point B. Try sending a TCP packet from computer 1 to computer 3 to reveal a flag. And we can see that this has already been set up. We'll send the data of hi and go ahead and send the packet. And we can see that this is actually broken down in the network log as well. So first we have the connection being established. we're actually confirming the connection and then sending back the ACK packet, and then we're sending our data itself. And we'll go and watch it in action up here. And it should be almost done. And there we go. Let's go ahead. It looks like my flag didn't show up, but we'll play with that in just a moment. How many handshake entries are there in the network log? Let's see. So we have 1, 2, 3, 4, 5. So it should be 5. And if not, I will double check my notes. And it didn't look like the flag showed up. Let me go ahead and play with this, and we'll see what happens. All right, there we go. So if the flag doesn't show up, just try sending an empty packet from computer 1 to computer 3 with a packet type of TCP. Let me go ahead and copy that, and I'll put it over here. You've got data. And there we go. That's going to do it for this room. As always, I will have the Tryhackme Discord and the subreddit linked in the video description below. Check those out if you have any questions. But otherwise, until next time, happy hacking.